Okay, thank you. Thank you, everyone, for your patience. On behalf of CEMA Africa, I'd like to welcome you to today's webinar on Science Runs on Software. I'm Annie Njanja, a communication specialist and your moderator today. It is great that you've taken time to join us for this important discussion on the growing role of scientific computing in research and innovation. Today's webinar will explore the growing importance of scientific computing, career opportunities, including research, software engineering, and the responsible use of AI in scientific software development. And we are happy to have Dr. Paul Korir, a senior research fellow at CEMA, take us through this session. Paul is a scientific engineer. Paul is a scientist, an engineer, an educator who has spent most of his career building high-performance bioinformatic data systems to leading regional training programs. And we will post more about Paul on the chat, so be on the lookout for that. Before I invite him, just a reminder, we are recording the session and it will be available later on CEMA YouTube channel. Also, we will have a Q&A session after the main session, but feel free to post your questions through the chat and during the presentation. With that, it is my pleasure to introduce our speaker, Dr. Paul Korir. Karibu.
Asante sana, just to check that you can hear me loud and clear.
Loud and clear. All good.
Okay, very good. Thank you for your thumbs up, and thank you, Annie, for that very kind introduction. And thank you for giving me this opportunity to talk about something that I'm very passionate about and that I'd like to champion and get more people to be aware of. So I want to talk to you today about science runs on software, but hopefully I'm going to paint a slightly wider picture of how that actually works. So it's not just about the software. There is underneath an ecosystem, and increasingly, this ecosystem is being enabled by generative AI as a very powerful tool to accelerate the application of software to science. Now, as I begin, I want to start with a story, and I want to tell you the story of a gentleman called Louis Fry Richardson. So Louis Fry Richardson was a climatologist, a meteorologist, and he studied fluid dynamics, and he had a very good understanding of fluid dynamics. He lived in the first part of the last century, and he made some very interesting contributions. Now, this is what the story goes as follows. So at the time when he was doing his work, he wanted to solve a problem of predicting weather. And it was what he seemed to him like something that should be very easy to do. Why? Because the equations that governed or that explained the movement of the wind and the clouds and how that translates into rainfall and snow or changes in sunshine were very well understood. They were very clearly defined. And so what he said was, hey, if I have the data, I can actually do predictions. So he got some historical data for which he knew the ground truth, and he set out to do this calculation. Now, apparently, these are very long calculations. They take a long time to compute. And what Mr. Richardson actually discovered is it took him about 2 months to do this calculation. And at the end of the 2 months, lo and behold, he had an answer that he could compare against the truth. So this was a day in the past for which the weather conditions were actually well known. So he was trying to do a prediction of a 6-hour window. And so from his analysis, unfortunately, his answer was incorrect. But it wasn't incorrect for the reason you'd suppose. It was incorrect just because of the volume of the computation that was required. And from this experience, he left his experience with a vision. And his vision was, how can we make weather prediction tractable? How can we make it possible to do calculations about weather? Now, in order for it took him months, we shorten this to And so he came to vision, and so I'm going to sketch here on the screen so that you can actually see what he had. So he had this idea of a building, a very big building, in which the map of the globe was projected across the walls of this big building from the inside. So you can imagine you're standing inside. So this here is the building. Let me just mark it for you. So this here is the building. So you have these are the walls of the building. And projected on the walls are the different countries. So for example, this is Europe here, right here is Europe, and you can see parts of Africa here. And right at the center of this building, right in the middle, would be a tower. So this is our tower here. And you'd have an individual standing here with a way to focus attention on certain parts of the world. So, for example, he had, let's say, some lights here, some floodlights, and he would illuminate on a certain part of the world. And at that particular part of the world, for every part of the world, there was a group of individuals who are very good at calculating. And at the time, these were called calculators. So these calculators would take the data that they had and then very quickly crunch the numbers for that part of the world. And then later on, the person at the center here, sort of like a conductor in an orchestra. So this person would then shine the light at a different part of the wall. And again, you'd have a group of people who are there, and those people would do the calculation at that part. Okay, so in this way, by assembling all these people, you could actually build a cluster computer. So remember this word is a useful word, and we may come to it later on. But this was his idea of how to calculate, how to make predictions of the weather. Now, it turns out that this approach wasn't really realized, and the reason for that is because there are a couple of people who came up with a better solution. So if you've heard of a man called John von Neumann, together with others at Princeton, and working on one of the very early forms of computers, one called ENIAC, took that same data and ran it through the machine, and they were able to predict what the weather was. In fact, they did this in a matter of minutes. It took him a very short time to do these calculations. And so Louis Fry Richardson and John von Neumann are what we could call the progenitors or the early versions of scientific computational scientists. And that is where the key points about this presentation. I'm going to mention 3 key ideas in this presentation that I hope I shall leave you with. The first idea is this idea about scientific computing. I want to present it to you as a tool. In fact, not just any tool, but a very pivotal tool in today's science. Like, you need scientific computing in order for you to succeed in research. The second thing I want to present to you, if you've never really thought about this, it has never crossed your mind, and it's likely that it wouldn't have crossed your mind, is that scientific computing, there is a field within scientific computing called research software engineering. So you know about researchers, we know about software engineers. Well, there is this new hybrid called research software engineer. And I'm going to tell you a little bit more about it. And the third thing that I want you to leave from this conversation is how Gen AI has really changed the rules on how scientific software and software in general is carried out. And this, we will see within a couple of years that this will have an impact on science. So the first idea, I want to label this as a pillar, that scientific computing has become a de facto pillar of science. And you'll see this diagram again. So this is a hybrid between a scientist and a software developer, which is what I'm calling a research software engineer. So let's start off with part 1. I'm going to talk a little bit about scientific computing. What is scientific computing? What does it entail? And what can we actually do with scientific computing? Now, it used to be the case that science was founded on 2 big pillars. The first pillar was that of experiments. And this goes way, way back from the very early days of science, that science required observation. So the people who are scientists were those who made observations in a systematic fashion. And through this systematic fashion, they were able to come up with conclusions and discover new knowledge about the world. So observations, whether these are for natural phenomena or not, at the end of the day, it's about observing the real world. And scientific experiments are where one can set up a controlled set of observations, where you limit the number of things that can change in order for you to make conclusions about some natural or social or other phenomenon. So that is pillar number one, experiments. Now, what Newton and a lot of those who came before him showed was that it is possible to do mental experiments, theoretical approaches. And Newton did this to a very large degree in analyzing the heavenly bodies. Now, this is not just Newton who did this. There are people before him like Kepler, Copernicus, and many others who came before that, who had, using mathematics and abstract reasoning, no experimentation, you cannot experiment on heavenly bodies, they were able to come up with valid conclusions, which form a lot of the bedrock of science today, science and engineering. So this is the second pillar. First pillar being experiments, and the second pillar being theoretical approaches. And I hope from the story that I started off with that you will appreciate that scientific computing has now become the third pillar. In other words, there are certain things that can only be discerned using these computational machines. So numerical simulations which require computational machinery. And I think it's very important to think about computers not as brains, which is, in my opinion, the wrong analogy, but really as machines, because they manipulate physical entities at a very low level. So scientific computing really is an essential part. And so what is scientific computing? So, ladies and gentlemen, I put it to you that scientific computing is an integration of a number of factors, and by bringing them together, we then get this emergent thing called scientific computing. It's not hardware on its own. A lot of people think scientific computing is just about high performance computing or AI acceleration. And that is one aspect of that. So there are different flavors of compute. A lot of people and interconnect computers. And that is definitely one important aspect of it. And some people think it's about the software that is written and disregard where the software actually runs. And well, some people think that it is about the skill set that is behind a lot of these factors. And I argue that it is actually an integration of all these factors. And I think for Africa in particular, scientific computing is a big, big opportunity as an engine of growth, both for the scientific and for economic advancement. I could go into a much longer explanation of how this actually works out, but suffice it to say that scientific computing, I think, is a big opportunity for the continent. And in fact, it fits in with some of the visions around Africa and the future for Africa that you would see when you look at the African Union's Agenda 2063 or the current the Science, Technology and Innovation Strategy up to 2034, called STISA 2034. So scientific computing is an integration of factors, and it produces something that really doesn't exist in any one of these on their own. Unfortunately, Africa is not doing very well when it comes to scientific computing. And so this is the results from a study that's been carried out across Africa, polling institutions to understand what their readiness in scientific computing is. And as you can see, there seems to be a bit of a desert of scientific computing across the east and the west of the continent. South Africa is very well endowed when it comes to scientific computing infrastructure, as well as skill sets and training. And you see across these various factors, AI acceleration, CPU compute, software practices, connectivity, Africa is really not well established or developed. And therefore, there is a big opportunity for growth. So if you're at the really early stages of deciding your career direction, I think scientific computing would really be a useful avenue for you to give thought to. And as I'll talk about in the next section, I think the opportunities are across different domains. So when it comes to scientific computing, I think if you want to be involved in science, scientific computing is no longer an option. Okay, it's not something that is something that you could consider. It is a requirement. It is necessary. You cannot be part of the scientific game without it. And a lot of the experimental data that we see nowadays requires some form of scientific computing. And we shouldn't think of it as something that's nice to have. We should think about it as a necessary piece of infrastructure and practices for us to do science. So if Africa is lagging behind in this infrastructure and in these practices, we really need to invest in that and put a lot more thought into that. Now, let's turn our attention to just one of the 5 factors that are listed here. And when we talk about human capital, we're really talking about skill set. And I want to frame this skill set from the point of view of a particular discipline that's emerging. So research software engineering is still in its early days, still a relatively new discipline. It first emerged someone mentioned this in a paper in 2010, incidentally to someone from Princeton, just like John von Neumann. And the term was first formally used in the UK. So the UK has an organization called the Software Sustainability Institute. You can go to their website, software.ac.uk, where they try and champion the development of this field, the UK and wider afield. And there's now a society for research software engineering, just like you have the Institute of Electronic Engineers, IEEE. So the Society for Research Software Engineering says that this is the combination of professional software engineering expertise with an understanding of research. And the reason why this is important is while traditional software engineering has usually emerged from people who've got a background in computer science or software engineering, well, this particular field requires people who have a background in some scientific domain. It can be the hard sciences like physics and chemistry and the engineering sciences, as well as what are more the artistic and a lot of data in those fields, as well as in other fields such as in climate and in health, and which are applications or professional disciplines. So essentially, it's a couple of things working here together, where you have domain knowledge, some domain, together with this professional skill of building quality software, together with teamwork. I think it's always important to realize that the strength doesn't come from individuals, it comes from people working together. And so this is what I want to sort of convey. While scientists produce knowledge, that is their bread and butter. That is what they are known for. And software engineers produce reliable software tools. Well, this new breed, this in between of a research software engineer, is someone who enables reliable research software tools or tools that allow you to give scientific insight. And if you're just starting your career, I invite you to consider that this could be an option for you. Now, the domains of application I've already spoken about, the science and engineering. So we have the hard sciences, engineering sciences, as well as biology. In fact, biology is one of the biggest applications of scientific computing through bioinformatics, structural biology. But you also have astronomy. For the longest time has been a source of volumes of data, especially with the kind of telescopes that they have. But as I mentioned, the arts and the social sciences, so linguistics has become a very, very important part of research. And we see this now with fields like, with tools like large language models, which have emerged because of the insights of the structure of languages. But the same applies with social networks and social sciences. Social networks usually have large volumes of data and can give you insights which can be applicable towards other fields like health. And then climate and health, the climate sciences are also a very big source of data that can be integrated across different fields, as well as health. We saw this during COVID-19, how data was such an important input for us to generate insights. Now at CEMA, we have several different disciplines working together to try and get insights out of data. There are teams that are working on epidemiological models and trying to understand diseases, their occurrence, their prevalence, the incidence of the data, but integrating that data with government data such as the administrative units, as well as taking into account geostatistical techniques like whether diseases are associated with climate events. And this can then be applied together with different economic models or transmission models, how people integrate and interact with each other, which can give insights on precision public health. So this is really the forte of CEMA and the kind of data that we work with. So we do have a lot of scientific computing that's taking place within CEMA, even though we may rarely refer to it that way. So now I want to shift to the last part of my presentation. So we've talked a bit about how scientific computing is this integration, and we've zoomed into one particular part, which is research software engineering, which is a human capital side. However, now I want to try and ask the question, how then can AI be used to boost research software engineering? And I think we need to be quite unabashed about this. We need to be quite bold in taking advantage of the tools that have been developed to accelerate our development of such tools. And the starting point for this conversation is really about what generative AI has done. Generative AI has really rewritten the rule books, and the rules have changed so substantially that people are still trying to find their place in this new sort of technological order. It's no longer the same game. And if you are trying to do stuff that you are very successful on 5 or 6 or 7 or 10 years ago, well, I would invite you to think on how can you rewrite the rules? How can you adapt to the new rules, and how things have changed? So how has Gen AI changed the rules? So there are a couple of things here, and I invite you to just think about these, especially in context of what you do right now. For me, one of the things that I've found has changed dramatically is how I learn. So traditionally, how we learn is we would find a resource where you can take a course or over a certain period. The emergence of massive online open courses, MOOCs, was very exciting from the less about 2011, 2012, because Coursera was born in 2012, and it really started this movement of people learning online. But the reality has been that MOOCs have been a bit of a disappointment. If you look at the numbers, only between 4 and 7% of people actually complete courses in MOOCs. So that's one. Another frightening statistic is up to 70% of individuals who sign up for a MOOC never even attend the first class. So in as much as the technology is available, so the technology for MOOCs is available for learning online organized material, the reality is that a lot of people do not really take up that learning. And this is where generative AI really makes a difference, because it's now possible to have your own tutor. And you see this with certain institutions. For example, Tsinghua University in China, which is the biggest university in China, one of the top universities in the world, have provided for all of their students a personalized tutor. And this tutor learns about the students' weaknesses, areas for growth, and can support the students to actually then develop their individual skill. So I think one of the really exciting things about using generative AI is that we can now develop intuition. It's no longer about rote learning, but you can really drill down through this personalized attention and tutoring that you can get from Gen AI. The second is, I think, how we write. If you're like me, I always find writing very difficult because my mind scatters all over the place. And that scattering is good for brainstorming and ideation and being creative, but it's not so good for writing. Writing requires that you are focused for a certain period of time and that you progress the content almost in a linear way. Well, Gen AI can take a lot of that burden so that you can do most of the thinking and hand it over to Gen AI to really polish for you the writing. And one of the cool things you can do with Gen AI is you can actually guide it on the style of writing. So if you have a particular favorite author, and that author has probably been absorbed into Gen AI, and Gen AI understands that author styling, then you can. If you look at how we used to search for information on the web, and how you had to know how to adjust your search terms, a lot of the way we would search traditionally was we would use keywords. But these keywords would have different weights depending on the term. So, for example, if you are doing a search for something that was very easily available on Google or on Bing or on DuckDuckGo, that particular term would dominate over other terms. And so therefore, you kind of had to learn this meta language, this search language where you'd use quotation marks and subtraction signs and end words to sort of filter your research. And of course, Google has evolved with time. But now the really cool thing about generative AI is you can ask a question and the answer will be tailored just for you, just for that particular instance. And you can even then have a second question, and that question can then really drill down. And I don't have to preach to all of you, but you do understand that this has a massive, massive impact on how we find information. It's far easier to find information. And then I think for those who are technically oriented, and I would hope that would be most of you, how we write code has really, really changed. Because one of the, and I'll point this out later on, one of the areas where generative AI really, really excels is in presenting code. You are no longer confined to the programming language that you're trained on. You can work on absolutely any programming language, even one that you have only just heard of. You can actually generate some useful code in that language. So these are some of what I think are the biggest changes. But what are the characteristics that we need to be aware of? And these are instrumental for you as you begin as you work with Gen AI. Everybody knows about hallucinations. I don't need to drill down into that. Introducing spurious content. But two others which I think are not as well spoken about are psychophancy. So there's a paper that was published in Science talking about how AI has a tendency to praise and make you feel like you're smarter than you are. And that can be a bit dangerous because you can walk around with the impression that you are smarter than you are, when in reality, what the AI is actually doing is sort of spurring you on and making you feel like you are smarter. And I'll give you some tricks on how to actually fix these. But the third problem rather, is that unfortunately, these tools have got a very limited memory, which is called the context window, what they're able to reference at any one time. And that becomes an issue which then leads to hallucinations once you exceed the boundaries of this context window. But as I said before, that the coding quality is really good. And I think one of the things I learned is that the code quality is actually professional level. So you can get professional quality code using generative AI, even for a language that you're not familiar with. So what does this require of us? And I think that this, at the moment, seems to be the killer application. It is what is driving a lot of this agentic AI. So I want to give you 5 tips, which I hope will be helpful as you think about how do I begin to explore this field called research software engineering. How do I use AI to augment my ability in that? And I think these 5 tips could be useful for you. So the first thing, which to sort of combat the hallucination and flattery, is to have an adversarial personalization prompt. So if you all the different tools that we have for generative AI, they have a part where you can give instructions. So for example, for Claude, it has a part where you can give it some instructions, which it will use time and time again. And one thing that I like to do is to tell it to be rigorous and not to flatter me. Be rigorous, don't flatter, challenge every position, ground responses in evidence, provide credible references when available. And you'd be surprised how mean the AI starts to become. Like it starts challenging and pointing out flaws. Sometimes, even after it's given me a critique, I ask it, it sounds like you're being very, very, you're praising me a lot. Give me a more realistic response. And it says, well, yes, it is true that I have been praising you a lot. And then it goes on to give me a more grounded critique. So this is the first trick that I think really helps to at least position you in a proper way. The second thing, which I think is so important, is you need to master the fundamentals. And the fundamentals, if you're going into research software engineering as a discipline, there are 2 distinct fundamentals here. The fundamentals, the first one has to do with the software engineering itself. So, you really can't get a lot out of Gen AI if you're not at that level where you can scrutinize what it's given you. And therefore, I think it's important to understand some of the terms or some of the practices within this discipline. Doesn't mean that you have to be an expert, but at least be aware of what can you expect so that you can put that into your prompts when you're generating output. But I think it's the same thing with your domain. So if you're using it to write software in physics, you really need to understand the fundamentals of that discipline. If you're using it in genomics, you need to know what is sensible within a genomics pipeline or within genomics data. So that's the second thing, for you to at least maintain some control and steer the Gen AI towards giving you the kind of outputs that you want. And this sort of is related to the third point here. You may have seen some of these badges on software like GitHub repositories. These are usually an indication. They help you figure out whether the software is been written to a certain standard. And therefore, understanding how to make code test itself. So here you can see, like on the screen, let me just mark it for you, the ones which are, like these ones here about code coverage. Code coverage is really an important tool for you to use and ensure that your tool is, as you add more and more functionality, you do not lose the functionality from before in order to avoid sort of the consequences of hallucination. So having some of these testing practices anchors your code and avoids it from drifting. If there's any one particular skill I'd ask you to develop, this is it, this rigorous testing. I cannot emphasize this enough. The fourth thing I would suggest to you would be to try your hand on using agentic coding tools. Now, unfortunately, these tend not to be free, and it's because they actually use a lot of the resources in the background. But learning how to work with them, and in particular, I'd ask you to look at something called specification-driven development, just as one avenue. What SDD allows you to do is take advantage of the tools as best as you can while managing that limited context. So if you look for anything after this call, look for specification-driven development. That's a really powerful tool. And the final suggestion I would make to you is to elevate usability. So this is the tools I mentioned, elevate usability. And what I mean by this is software is always designed for a certain group of people. You need to understand what their needs are. And that means in your process, devote a disproportionately large amount of time towards understanding the user needs, because that goes a long way in improving their experience, as well as giving you feedback that can then be integrated to give them a much better experience. And that feeds into the design, whatever design you're going to produce. But elevating usability, given that these tools have shrunk the amount of time now we should spend on development, we should devote much more of that effort towards understanding users. What's called technology anthropology. Just like traditionally, anthropologists would travel and visit a remote tribe and understand what their language is, their practices, their foods, how their culture functions. I think it's the same thing that is required within software, especially if you're going to be developing research software. So just to bring it back home, these are the key 3 points, and I hope I've covered them in a way that has convinced you that one, scientific computing is not just about hardware, but it's about this integration. You could have a career as a research software engineer. If you're working in a particular domain, you could elevate that domain by developing software skills that improve the kind of software that's available. And the third point is GenAI has rewritten the rules, and we have to adapt to that change in the rules. I think that's all from my presentation, and I'm going to stop here. I'm happy to take any questions or comments or any contradictions that you may have. Thank you very much.
Thank you, Paul, for that presentation. Really insightful. So we open the floor to questions. Guys, if you have any question, you can unmute yourself or post in the chat, and Paul will be happy to address that. And also, just to see if we've understood some of the things that Paul has talked about, especially on the pillars. I'm posting a question on chat, and feel free to answer. And Paul, maybe as we wait for the questions to come in, when we are using these tools, especially to generate code and to make our work easier and faster, what do you feel about transparency in terms of like, at the end of using these tools, are we like for researchers, are they like required to say we actually used code, let's say cloud or ChatGPT to make our work easier or faster?
That's a really, really good question. So I'm going to answer it on multiple fronts. One is, as I said, the game has changed, and anyone who insists on doing things the old way, they're free to do so, but you'll begin to feel the effects of being left out and being left behind. So just from a pragmatic point of view, I think we shouldn't be shy about it. I was on a call not too long ago where there were a couple of people who they were mocking the kind of code that comes from these tools. And I think that that's a wrong attitude. I think we should embrace these tools. We should learn how to use them, because there's also a learning curve. It's not that just because they can generate code that it's easy to use. The way a lot of these tools are used, it's kind of obvious when someone uses them. So, for example, if you're going to use a tool like Claude or Codex or Gemini CLI, what you're typically advised to do is to include within the repository a set of files, and these files are sort of a declaration that you're already using. So there's a file called agents.md, which governs how these agents will work on your code base. So you can't really hide it. And also, it's easy to tell, when someone looks at your commits, they can see this is volumes of code being added within very short spaces of time. Having said that, I don't think people should be shy about it. I think people should be open to saying that they have used GenAI, so that we can learn from one another how to use these tools much more efficiently and much more effectively. These tools are very expensive to use. All of them, I think, require paid access. Mm-hmm. And therefore, we should yeah, we should use them and use them to our advantage as fast as we can. So don't be shy about using them. Uh, make it clear that you've used them, and learn how to use them as best as you can. A great question.
Awesome. Guys, the floor is yours. Ask questions. If you have any comments, also feel free. And be on the lookout for
Okay, I see someone else.
Sorry?
Could you comment on how AI has affected how we access credible news? That's a good question. So I'm not an expert on now. Maybe this is something better for Annie to answer. But I'll just give you my 2 cents. There have been historically, or I mean, traditionally, reputable sources. So, for example, the BBC, CNN, local news channels, if they're following their journalistic tradition, then they would declare if they use Gen AI. But ideally, they would be the sources of reliable and credible news, and we should be able to rely on them. But I'm not an expert on media and news. Maybe Annie, you can chip in on that.
Yeah, so as you said, Paul, I agree. So I think the tools have really made it so important for us to no longer just Google when we are looking for information, but go on the sites themselves and look for the credible news. And most of these platforms are also free, like BBC, Reuters. You always get this if it's breaking news or events that have wide coverage. You'll always get information on that. But I think the tools have really made a case for original reporting and journalists' work. So I think you'll always be redirected to the news sites, and I think that's where we should be getting our news as you know, as we get flooded by all these tools and all the information. Yeah. Okay. So we have
How
another.
can we grade students as opposed to grading AI? This is a great question. Actually, incidentally, the person who asked the question, we had the same conversation. So I think we should fight fire with fire. And what I mean by this is students should be free. I think this is just my opinion. Students should be free to hand in whatever they want, but we can then build tools using the same Gen AI, which can then grade what they submit. So here's an example. So I have a class of students. Let's say I have 350 students in my class. I will not be able to police all their submissions. But suppose there was a tool such that where they do the submission, so they go to some website, they upload their content. Immediately they upload the content, they have to sit a test for what they've submitted. Because it's generative. Like you can submit the content and you can generate multiple choice questions from that content. And they have a 30-minute duration of 15 minutes to answer, a certain set of multiple choice questions. And that will be their grade. So even if they submit something that they didn't write, they have to study it in order for them to learn something out of it. So that's what I think. I think we should fight fire with fire. We should not be shy about using Gen AI in the grading system. Of course, it means that these have to be tools that have been properly designed, properly structured, properly tested. But that's the opportunity, I think, to fight fire with fire. Here's another question. Are there any keys to free resources, reading, watching, that one can expect to understand this developing field deeper? We may want to join this field. Well, there are hundreds of resources online. The generative AI resources, the tools themselves are a wonderful resource. But as I said, you have to calibrate them by adding those personalization adversarial prompts so that you get a more reliable input. And you can use multiple tools at the same time and just gauge the answers that they give you. But there are also many free online courses, tons of videos on YouTube. So there is a lot of information. Just search online and you should be able to find that. If you want, I can get a set of resources that maybe can be provided on the description of the video once this is posted on YouTube. that I can pass on to Annie. Which of the following is not a scientific? Oh, here's a question for you. Which of the following is not a pillar? Or that's for you to answer. As in AI flatters, so how can one be sure if you tailor your answers to rigor, thoroughness, how can we be sure that it is being objective, rigorous, and not just rigorously flattering? So that's what one within that prompt, if you recall, I said provide references. I tend to try and fall back on using resources from, let's say, a site like Google Scholar. So whenever I ask Gen AI, I ask it, can you also give me a reference? Then I can check that reference. I can see, is that a highly cited reference? What is the content of that reference? So there is ground truth, but you need to do some work in order to extract information from that ground truth. But as I said, you really need to make sure that your Gen AI is not flattering you. So just start with the prompt. That really helps. What do you think is a long-term effect of using AI, especially in learning? This is a great question. There are two schools of thought and two approaches. One is if people naively just use the AI without thinking and assuming that the content from the AI is correct, that will undermine your ability to think. And ultimately, your ability to think is really your value, your value as an academic. But again, we can fight fire with fire. One of the things I love to use is Notebook LM. So Notebook LM, in case you've not heard of it, I'm going to type it in the chat. Notebook LM. I think it's .google.com. And this is free. At least there's a certain free tier. You can take a certain passage, upload it into Notebook LM, and you can ask it, can you give me multiple choice questions to test my knowledge? Can you give me flashcards? Can you give me other sources? So while it is possible to abuse these tools and undermine your learning, like it's precisely the same tools that can really augment and expand your learning. If you want to develop intuition, they are very, very powerful for that. So I think at the end of the day, it boils down to the individual. How are you going to use them? If you looked at the population in general, there will always be people who want to abuse these tools. But how do you want to use it as an individual? Are there any chances that the tools like Claude can sub that by generating code that will break your purposes or insecure codes after leaving a backdoor? So that's a very good question. Now, so your question essentially is, if I ask Claude to generate code, can it unknowingly give me code that will break my system? And I don't suppose it would. And this is the reason why I said at least get some knowledge in that domain. So for example, if it gives you code in Rust, how can you run the code in a way that you can test it? Because usually it will test it on its own. It has a sandbox. And these tools have teams who very aggressively test the output that they can give you. But you need some level of skill to independently test and make sure that in a safe way that it doesn't break. So you don't want to be fooled and end up damaging your system or damaging your computer. So yes, I cannot vouch and say that there's 100% guarantee they'll never give you code that can sabotage your system. But at the same time, if you look at how these tools are built, and they provide a lot of information on their websites, the different stages that they go through when they're testing these tools, you will find that it's very unlikely to happen unintentionally. I think those are all the questions that have been asked so far.
Yes. Yep. Unless somebody else has another one pending. But I think that's it. Okay. Fight fire with fire. Hello. You're muted, Korir.
Yes, I'm muted. There's one other question by Samuel. How can someone reach you out? You can always contact me through CEMA. There's info@cema.africa, and they can forward that request to me if you wanted to discuss something in detail. info@cema.africa. I'll type it in the chat.
Okay. Thank you so much, Paul, for that captivating session. I think the takeaway is that don't be shy. These tools are there to be used. Just make sure you're also transparent about the usage. Thank you. Thank you so much for sharing how scientific computing continues to transform research and how emerging technologies like AI can be leveraged responsibly to advance scientific software development. On behalf of CEMA Africa Seminar Series, thank you for joining us today. Thank you so much, Paul, for taking the time. Guys, be on the lookout for our next seminar and the video recording on our YouTube channel. Thank you so much for attending. Have a nice rest of the week. Yeah, don't be shy, use it. Okay. Thank you.